Joris Peels, and I have the pleasure to welcome you today to this roundtable discussion. This is brought to you by Velo 3D, and Velo is doing this in conjunction with Smart Tech Analysis. My name is Joris Peels. I'm the VP of Consulting at Smart Tech Analysis, and we're here with a very experienced panel today to talk to you in this Innovators Roundtable about ditching DfAM and embracing design freedom. DfAM is an often discussed topic in 3D printing. Everybody's talking about design for additive manufacturing. And the idea is that we all have to learn how to design parts specifically for the additive manufacturing process in order to make these parts work. And this is a whole cottage industry, and that's a really, really important thing to be doing. But to what extent do we need to do DfAM? And to what extent is it, sometimes can we completely ignore it? And can we completely ignore it? Do we have to always design for the process? Do we have to always optimize for the process? Do we have to learn to design completely differently for additive manufacturing? Or in some cases, can we kind of stick to our guns and stick to our practices? And that's kind of what we're going to be discussing today. Now, we're going to be discussing this today with John Barnes. So John is, he's instrumental really in getting some 3D printed, from some of the first 3D printed parts aboard some commercial and not so commercial aircraft. And John's working at before at Honeywell and Lockheed and a couple of other companies. So I'd like to welcome you to the panel, John.
Thank you. It's great to be here.
And so what are your thoughts a little bit about, you're a consultant, so you come from aviation, and aviation has had a really like a leading role, but it's a really high compliance type of environment. So what are your thoughts on DfAM in additive manufacturing?
Yeah, so I think there's a couple topics there. You know, I know there's the people who make printers think about it very narrowly, and the people, you know, we look at it more from a requirement standpoint, and that kind of at the end of the day, this thing is going to meet the requirements for the aircraft, and then it's got to do a whole bunch of other things and probably be cheaper than the previous article. So, you know, I don't know that there's any way of getting around designing for manufacturing, and additive is a component of that. So I think these new technologies that are available that open up the design freedom are fantastic. But I don't, you know, I'll be the naysayer to ditching DfAM entirely. Spoiler alert. But I support the notion. But I think, you know, when we do the polls, about a third of the industry even defines DfAM the same way. And so we just take a very holistic view of it, which is you have to take into account everything that happens after it leaves the printer as well. Otherwise, you're going to be probably in a world of hurt.
Mm-hmm, mm-hmm. Oh, definitely. And I think that's really quite interesting. So now we go to Jose Cordova, and Jose has also been working in 3D printing as trying to implement 3D printing at well, they call themselves MITI or Mohawk.
Mohawk Innovative Technology, yes.
Yeah, or MITI is kind of the internal kind of name for the cool people, right? And so Mohawk makes turbo machinery, very, very specific turbo machinery for DARPA and NASA and customers like that. And so they're using 3D printing in a very, very exacting application as well. And how did you guys come to be using 3D printing in your company?
It's actually an interesting story. We were developing a very high pressure, high temperature compressor for supercritical CO2 application. Supercritical CO2 is an extremely high pressure gas, and it has a lot of nasty characteristics, corrosive. It's difficult to handle in general, but what it does is it packs a lot of punch in a lot of in a very small package. So you can make very small turbo machinery to deliver a lot of power when you use supercritical CO2 as a working fluid. And very quickly, the problem we found was that the concept of thrust management, in the sense that your axis of rotation is, or rather your rotor is constrained in place by axial, what we call thrust bearings. And because of the pressures at which we handle the gas, the thrust management was becoming extremely difficult, and the shaft wanted to be shoved in one direction of the machine. So we ended up designing this very complicated housing that could accommodate a bunch of seals to isolate different pressure zones. And once the design was complete, what we found was that it was essentially impossible to fabricate. We approached multiple vendors that we had worked with in the past to fabricate it from traditional techniques like casting and machining and welding. And what we found is that in the best of cases, this housing, a single housing of an overall compressor system, was going to cost us upwards of $60,000 and probably as long as 6 months of fabrication time, both of which would blow our budget and our timeline out of the sky. So very reluctantly, my boss accepted that we could explore 3D printing. Nothing that we have really done in any serious way in the company before. We have done a couple of components before. I'm talking about maybe 10 years ago when it was a very green field of research, really. And one of my colleagues actually located Velo, and it was the collaboration with Velo that opened our eyes to the large new field of possibilities when it came to really design freedom. And this housing that was essentially impossible to build, incorporating seals and bearings and the intake and outlet volute all in one piece. Actually, Zach Murphy and Zach Walton and their engineers helped us basically modify our drawings to fit. These were very small modifications to better take advantage of the 3D printing process, and they delivered a housing for us in about 2 weeks for less than $15,000. So I was sold at that point.
Okay. All right. Another person who has sold on 3D printing, but also was probably perked up when seals were being discussed is Steve Freitas. And Steve is at IMI or IMI Critical, which is part of a company that makes valves, all sorts of really, really demanding valves, industrial valves for power plants and all sorts of applications like that. They make over 250,000 customized valves. And they also actually have, as IMI Critical, they actually have a kind of refit through offering where they will redesign and print your existing old valve, if it's from them or from maybe somebody else, or maybe you don't know who it's from. They'll redesign and remake this old valve, which is something I'm really excited at. And how'd you guys come to doing that? Because that sounds like a really exotic application for a lot of people to redesign existing valves.
Yeah, thanks, Joris. We've been doing this, we call retrofit program for actually 40 or 50 years, but we were constrained by our legacy manufacturing technique and design. So this is, we call a drag disc. It's got this plurality of tortuous flow paths. And these get raised into we call a disc stack here. And this has been a good technology for 40 or 50 years, but it's relatively bulky. And we also found that it doesn't scale down well to small sizes, that in small sizes doesn't provide the precision of control we'd like. So we began looking into a better technology about 10 years ago, and we came across the early days of 3D printing. And we, as long ago as 2008, began building our first 3D printed parts. And at that time, we didn't know how to DfAM. We didn't know what to design. So we were kind of hit and miss for many years. And then I think a few years ago, we had a breakthrough on how to achieve that process. And we found that with 3D printing, we could not only get better control consistency for our customers, but also unlock a wide range of new shapes, forms, installation options, which really provided the capability to do this retrofit or refit program in a wide variety of situations that we couldn't even accept in the past. So it's really been transformative to our business in the last, I would say, couple of years, especially.
With the transformative, as in you're actually getting parts out the door and making money off of the parts, or not like as?
Oh yeah, we have a significant business doing the refit retrofit program, and we've also began incorporating the technology into what I call standard high pressure products, which are used at up to 100 degrees Fahrenheit and up to 4,000 psi, and we've routinely shipped 3D printed parts to customers for these applications. And, you know, here's some examples. I'm not sure you guys can see, but you know, this is obviously a 3D printed part with these, you know, elaborate shapes, which we couldn't do in the past. And
this is like one holistic part, and that's one holistic part, right? That one.
Exactly. Yes. Yeah. And because we can make a single monolithic part, we eliminate about 20 internal process steps, which is a huge benefit to the business. We get a more consistent process. And because the part is structurally unitized, we can put it places we couldn't put before, new applications, new configurations, new assembly types. And that's changed how we approach customer problems and given us a whole set of new tools to help customers make their plants operate more efficiently and reliably.
You mentioned something called control consistency. Is that like a specific term for, or?
Yeah, so one thing that's done both in power plants and oil and gas plants is, particularly power plants, there's an application called a spray valve where water is injected into a steam boiler to control the boiler funnel temperature. And with our legacy process, we just couldn't get the control accuracy we needed. You know, you turn the knob a little bit and the flow jumps up by a lot more than you wanted. But with 3D printing, we can actually get extremely precise improvements in flow control accuracy. And that helps the customers to run the plants more efficiently, but also more reliably, because it eliminates temperature swings, which contribute to stress cracks in the downstream boiler components. And so we've taken this to market and are offering this to customers as a benefit. And we also found out, like Jose, it's not only is it better, it's also lower cost. It gets rid of NCMRs, it gets rid of discrepancies, it gets rid of warranties, it gets rid of customer complaints. It's a huge advantage for our customers and ourselves.
Okay, good to hear. Well, one person who's super good, happy to hear that is Zach. Zach Murphy is a salesperson, but do not hold it against him. He's also a doctor in with aerospace engineering or something like that, or and he's generally knows what he's talking about, which is also really refreshing. So welcome, Zach.
Thanks. Yeah, I appreciate that intro. I try to pretend like I know what I'm talking about sometimes, but
you're doing a great job.
It's tough with a panel like this, to be honest. I'm happy to be here and be talking about what we've kind of enabled.
Okay. So let's start with John, because John was talking first about the definitions of DfAM, and that's I think is a really important place to start. So, you know, for the interest of everyone, how would we define DfAM, or how would we just like demarcate it to a certain degree so that we know what we're talking about? You want to try to stab at that, John?
Sure. So we define it as, you know, what does your part have to do at the end of the day? So for most aerospace, really it comes down to being able to inspect the part. If you can't inspect the part, it doesn't matter what you've made. So we tend to, that needs to be taken into the design. You know, can you inspect this part when you're finished with it and find what you need to find? And if you don't take that into account in the design, you know, that's how we work with it with our customers. And generally we find that there's a whole lot less surprises when you take that very holistic approach. How it comes out of the printer is obviously interesting, but ultimately it's got to do a bunch of other things. And so that's how we define it. And as I mentioned, you know, it's not widely accepted. And I think it was interesting when Steve was talking, you know, we break that into modify for additive as well as design for additive. And so, you know, modify is when you don't really have that design space that you can do whatever you want. But what I loved about that example was you open up when you go back to what actually the requirements are, you're now not limited to what was done previously, because we have a new tool now to manufacture with. And back when I was with the engine company, first we could make things that we couldn't design. Then the computing power went up and we could design things that we couldn't make. So now we're achieving parity again. So it's all goodness, but it's just like everything. If we don't speak from the same alphabet, you know, I think it's we're talking past each other.
No, I think that's good. That's why I wanted to start with this. I mean, I think, and what have traditionally been, if you look back at trying to qualify parts for aerospace in particular, which have been a kind of torturous journey, I think, for those who were involved. You know, what were the problems with DfAM there? I mean, you had some process constraints that were very limiting, right? Yeah,
outside of you know, a part that I had familiarity with. I mean, what it came down to is that we created a microstructure. This was not a powder bed process, but it created a microstructure that created shadows when you inspected it, and so it failed after spending a lot of money on it. So you don't want to do that too many times. So yeah, so that's. You know, like it sounds like everybody on this panel, you know, is nodding their head in agreement on that. So I'm not bringing anything that they don't already know.
Yeah, and a little bit back to Jose, like, so when you guys use, you're using also, like, you have a critical application also. If your part fails, it's a catastrophic failure every time, basically, in your business, right? I mean, there's
Every time.
yeah,
Absolutely.
there's no little failures in turbo machinery.
That's absolutely true. I will start first with the idea of cost, and I will revisit the idea of reliability and ability to inspect, because both of those are very important to us. I'll show you the types of impellers that, so after we succeeded with the housing, the thought came to us that maybe we could leverage 3D printing, additive manufacturing, to not just make exotic parts, but reduce cost. And why are we so interested in reduced cost? Obviously, because, everybody is, but specifically for us, the issue is that we make small production lots. Say we make 5 off or 10 at the outside, or 1-offs many times, because we're really a research and development firm. We don't manufacture en masse right now. So when you develop a first prototype for a compressor and an aluminum wheel of these characteristics, this has to rotate at 80,000 RPM in, I don't know, 200 degrees Celsius gas. This little guy in a small lot production can cost us upwards of $2,500 to $3,000 each. And that's after the non-recurring engineering charges. When you go to high temperature, a guy like this one, made out of Inconel 718 or René 41, a single impeller like this one can cost upwards of $20,000 each by traditional machining, 5-axis machining techniques. I'm saying traditional, but these are extremely advanced 5-axis machining techniques, obviously. So obviously, when you think about making millions of units, the economies of scale shrink down the cost potentially to maybe hundreds of dollars, even less per unit. But we are not there in the kind of equipment we make. We address the incipient solid oxide fuel cell machinery environment, for example, where we are making prototype units, where we're making deliveries of maybe 10 units a year, not just me, but us, but the solid oxide fuel cell companies. For example, same thing for NASA, same thing for Department of Defense. They want to try a few units. So to come to a customer and say, each unit is going to cost $500,000 just because the components alone are going to set me back $150,000, $160,000 makes no sense. So we're trying to reduce the cost of these prototypes or small lots. The stories of success, again, with Velo, we have developed replacements for these machine guys. These are machined by one of their CMs, again, with a lot of support directly from Zach Murphy early on and Zach Walton throughout most of these processes. And in addition to reduction of cost, imagine that we made about, I'm going to say 20 of these at an overall cost of maybe $300 a piece. That's not including the heat treatment, but say $320 to $330 a piece, $330 a piece. We have a new flexibility in that we normally do not deliver covered impellers in this scale turbo machinery because they're prohibitively expensive to make. So we usually stick to open. But now we have the choice. A covered impeller can buy us efficiency, compressor efficiency, which in certain applications, particularly on manned aerial vehicles, for example, every extra percent point in thermal efficiency means that your fuel payload or that your fuel, your available fuel is capable of a higher payload or a longer mission. So these are critically, anything we can get in terms of efficiency we'll take. And this has reduced the cost and increased the efficiency of our compressors and therefore of our gas turbine engines. Now, when it comes to reliability, when you cast parts, you have to trust that there's no porosity. It's very difficult. Even if you do X-ray analysis, it's very difficult to inspect these units. And when you use forgings, typical forged material that you machine, we usually assume that they are more reliable than castings simply because the forging process eliminates porosity, but you're still acting on faith. One of the most attractive things about what developed process provided us with was the ability to visually inspect, of course, with their automated equipment, every single layer of the printing process. And one of our earlier experiences this year was a batch of these impellers was actually halted by the printer itself when it detected that there was a defect in, there was what they call a Z line or a Y line or something like that. It was basically a groove where there was some contamination that was dragging the powder out of location and essentially leaving a groove in the print. This would have been impossible to predict or detect with the old style or the older approach to 3D printing, and definitely something that we would not have been able to find in a casting. And what this happens in the end, what this implies in the end is that this turbo machinery at the high velocity and the temperatures that it's operating, it will probably burst. And when a wheel this size bursts, it's not that big a deal because it's contained by the housing. It's ruin a machine, maybe all of your research project. But when a larger one bursts, it can liberate shrapnel and essentially be a grenade and destroy equipment and personnel. So for us, one of the most attractive features of a modern process that Velo has introduced is that they can inspect every layer of a print and guarantee that the matrix is going to be, or rather the material matrix is going to be flawless, right? So.
But theoretically, you could design and make things quicker, and you get to your part faster as well, because the print process is faster than casting and outsourcing all this stuff.
Oh, absolutely.
But how long would it take you to get to a new design or to get to a thing like that? Or does that change at all?
Well, now that we know how to, in iterations with Velo and the CMs, we have essentially defined our optimal process for delivering these units. Actually, I'm showing you here the third iteration of these impellers. We actually had a very first build that looked pretty good, but once you did the metrology, was a little skewed, a little crooked, not quite right. Then we did a next iteration where after we corrected for some of these distortions, we had issues of surface finish that was not satisfactory, particularly at the sharp edges that the blades need. And these third iterations became extremely satisfactory, actually. We are now working on another project with the Air Force on what we are calling now the fourth iteration, even though it's a separate project. We have identified a way to really even improve the surface finishing by a hone extrusion process that gets done after the 3D printing. And still it's enabled by the 3D printing process because the blades, or rather the wheels, are printed in a manner that allows us to take advantage of this hone extrusion. In a normal machined part where the blades are already gone, we would not be able to do that. So we are not only looking forward to geometrically accurate parts, we're looking forward to receiving parts with extremely good surface finishes as well. And all part of the, all enabled by this approach for 3D printing. Now, the entire design process, if you don't account for the aero design, which is, our engineers, depending on the application, designing an impeller like this could be anywhere between, 4 weeks to 12 weeks, depending on the challenge of the gas or the operating conditions. But turning that around from a first solid model to a 3D printed part, we're looking at about 2 to 3 weeks altogether. It was impossible before under traditional machining or casting or combination of those approaches.
Okay, thank you. And Steve, for you guys, what's your process if we're looking at it from a DfAM or design standpoint? I mean, let's say you have an idea, you want to do this. How do you go from this idea to actually having a qualified part, or what's your process?
It depends on the geometry of the final part. So what we've done over the years is built up a library of we call flow paths designs, which are optimized for additive manufacturing with different sizes, aspects, ratios, different arrangements of turns and things. And our engineers, we have a small team that's pretty good at arranging and configuring them very quickly. So we can actually get, if we get a well-defined geometry from the customer, an envelope, we can actually plug in the flow paths within a half day, get them released within a day or so, and get them out to our AM supplier pretty quickly, and turn around parts in a matter of a week or two. It's possible to do. The other possibility is that we have an all-new geometry that we haven't imagined before. And so then we still take the same library of flow paths, but we might manipulate them differently. For example, the parts I showed you are cylindrical parts. We're also now putting these flow paths into round parts, into spherical geometries, basically into ball valves, and arranging the flow paths kind of parallel to the ball valve flow path to create an all-new product for flow control. So this is kind of how we work. And then if it's an all-new geometry, we do additional steps, like we will do a CFD to check the flow path accuracy, build a plastic model, flow test it, build a metal subscale model, flow tested, then build the entire element, and if necessary, do additional mechanical integrity testing. So that's kind of our process and workflow on 3D printed parts.
But there used to be, like in the very beginning days, you used to on powder bed fusion have to maybe redesign a part 5 times for support structures or support planning and that kind of thing. Is that different now? Has that been ameliorated to a certain extent, or?
Yeah, I mean, I would say the first 7 years of pain, we just were blindly trying, radii and angles and what angle's good enough, and we would get what we would call it dropout. We'd get these little drops and burrs in the flow path. And we didn't know why it was there. Was it a machine setting? Was it something in the build process? And even our supplier couldn't help us. So I'd say in the last couple of years, we kind of figured out how to do it. And then we also have, I say, a stronger involvement of partners like Velo that are better able to guide us on what can and can't be done and what should and should not be done. And that's been really powerful. Then the other thing we have is we still have over 10,000 legacy parts with flat features, which cannot be printed in any kind of laser powder bed fusion, looking to one day apply better 3D printing technology to print those legacy parts without having to redesign 10,000 parts. So we see that as a future kind of end state for CCI.
Yeah, definitely. Then you could update everything, make the digital library the dream state. I think also.
The dream state. Yeah,
Simple
It'll
as
take
that.
a while. I think it'll take a while, but it's good. And then I think we have an audience question. I think that really kind of dovetails nicely with what Steve is saying. I mean, maybe you're listening to these guys and you think, oh, this could be interesting. And then what Wai Huang said is, what level of superiority would trigger you to choose AM? Would you choose AM when the part performance is only a little bit better than today's traditional processes, or does it have to be much better, 10 times? I think that's a really interesting question for Zach. And I hope I'm not throwing at you really blind there, Zach. But yeah, so that from a small part performance, so we always kind of like see a lot of cases where people say, we save 20% weight on a part. Is that enough? I mean, personally, I always quote the examples of like the acetabular cups and the surgical kind of things. We're saying we can do it cheaper than traditional manufacturing. We can make it lighter, less mass. We can make it faster. We can iterate faster. We can closer approximate the modulus of bone, right? And we can also then make the bone adhesion better. And these are like all advantages that stack up. And that's why I think if you see a lot of interest from the orthopedics community, it's like there's a ton of these advantages. So that's why orthopedics to me makes like a mega lot of sense. And when somebody just comes to me, oh, we want this lighter, I'm like, do you? I'm like, how badly do you want this lighter? And is that the only thing we can get from it? So what would you say about that? No, sorry.
I mean, I think this kind of goes back to John's original point, which is that if you're only talking about performance, like that's just one part of the total evaluation, right? And it comes down to the things that both Jose and Steve were referring to also, right? So there's the time to iterate, there's the kind of design cycle reduction, there's supply chain flexibility, being able to have this dream of distributed manufacturing. All of those things are individual pieces of this value proposition that when you put them together can make a very compelling case for additive manufacturing. I mean, just the difference that Jose was referring to between open and closed impellers is something that seems very subtle, right? But if you're producing turbo machinery, can really buy you quite a bit in terms of final system performance. So being able to really build exactly what you want is the end goal. And I think when we talk about eliminating design for additive manufacturing or DfAM, it's really around making sure that the primary considerations for what you're making are performance related, or are optimization of those end requirements, and not, majority dominated by what angles can I print, what quality of material can I get at the end of the day, can I certify it, right? There's all these kind of ancillary things that from an engineering perspective are very important, but are kind of not the primary focus of designing new systems or making retrofit parts. Those should be secondary considerations, and our goal as a company is to make sure they remain secondary, because they're kind of accounted for.
And if I could maybe tack on to that, I mean, so when we talk to companies, we break it up. We have this maturity model approach, and when you look at a level 2, that's kind of like, I have this part, I can't change it. It's going to look like this part, and that's your typical spares product. It's done. There's no chance to redesign it. That's where the flexibility, by removing the constraints that a typical printer puts on, really pays off. But ultimately, you get to the part consolidation, and then you get to some of these, you really can only make them with additive. But what Jose wasn't, I think he's being a little bit modest. I mean, everybody's always wanted to make a shrouded impeller, but there was no way to make a shrouded impeller. So, impellers have been around. Impellers take out stages of axial compressors and turbines. So that's phenomenal in and of itself. And so once you get to a performance, we always break it down into the typical things program managers care about: schedule, scope, and cost. Did I save any schedule? Did I save cost? Did I make things more risky? If I failed any of those things, I probably don't care. But I always go back to like the F-117 stealth fighter. Has anybody ever asked you how much it costs? Nobody cared, because it gave you something that nobody else could do.
Yeah. No, I think that's a very, very good point. But at the same time, I mean, this is also interesting. I mean, are we going to make AM quotidian, right? Or are we going to make it every day? Like, are we going to be making like $10 parts for Ford? Or are we going to be making those $1 million parts for satellites? Or is there like a happy medium where I'm really excited by Jose's story and Steve's story about something like Jose was mentioning cost a $300 part, right? Which these orthopedic implants are as well, a $300 part that is critical in some way. And I think that's kind of our area, our happiness point, where we still get to make sense, And so I've got a question of that's for Steve, I think. They're really interested in your 10,000 parts identification things. As Brent Kephart wants to know, is this a manual process to figure out which of the part candidates? Are you seeing good software to solve this? How far can software could take the 10,000 parts before you can do this? I think this is a question I get this so much from clients. They come in, the first is like, do you have a magical piece of software that that we can identify all the parts from inventory? And what I tell them is, give me a list of like an Excel sheet breakdown of your most expensive parts that are like 20 by 20 by 20 centimeters. And we'll start there.
Exactly.
That's my best methodology so far. But this is like the holy grail, I think, for a lot of people. But so Steve,
that's pretty much what I did, but we didn't use any software. I knew that we made lots of smallish parts for customers who didn't have material certification requirements, but wanted good performance. So I was unconstrained in the geometry I could use and how I could build it. So I just went to town on that several years ago. And these are our smallest parts. We big parts are as big as 42-inch diameter, 6 feet tall. So this became our stand. Once we had this, we put this in the field by the hundreds. Then people believe this could be done. It's real. Then we can start to scale up in size for other applications. Then start to think about higher temperatures. Then start to think about, well, what about an application which requires a higher level of certification and the customers always specify a certain bar for them? How do we handle that? So I started actually quite small and then built that as my base, because I knew my risk was low and I could always pull out of it quickly. If you start with the biggest thing, and Jose's nodding, he said, if you start with a 7-foot impeller, that's a big bet to start with, right? You don't want to take that bet probably. So that was been our successful model for this.
When your job's on the line.
More than that, yes. If you're lucky, your job, yeah.
No, exactly. I think that's a good thing. And are you, and is it, well, the question especially, is there another way? Do you know of another way to do this? Because I know there are software packages. I try to evaluate them. I mean, the bad answer for Brett, he doesn't want to hear this, but there's no magical fairy dust solution that can let you do this with like your parts inventory. And there's also all sorts of problems with files and permissions and doing this automated as well. So sorry about that. There's no magical solution, but there is, I think, well, there are some ways to get there, I think.
Yeah, I think if you think through what you produce today, who your current customers are, and maybe what your future customers are, and think, what am I making today? And what are their critical characteristics, their essential characteristics that I can or can't change? And if you know that and kind of start from that, like this customer doesn't need to have a 20-page certification document, I'll start there. Or as you said, it's a smaller part as opposed to say a 50-pound part. You know, you can make those kind of initial qualifications and then just involve stakeholders and other experts in discussion, I think is the best way to go. Because you may also discover some surprises you didn't anticipate by taking that journey and asking a few questions.
I thought it was interesting, Steve, when you hinted at it, but it was, I think you asked, like, why is this thing round to begin with? You know,
Yeah.
Maybe it doesn't have to be.
We actually built one where it was at the edge of the build tray. So we squared off the edges and we said, well, why can't it be? Why must it be round if it meets the requirements? So we shipped a part which was oblate, square on the edges, and it worked damn good, actually. So yeah, why not?
I think that's interesting. I think a lot of people are mentioning like certification and things like that, and qualification, these kind of things. These are very difficult topics. I mean, how do you deal with that on a software kind of way, or on a shop floor kind of way? Is that because that seems like it's quite a challenge for especially in like an ISO type environment, or kind of like a very critical type environment. How do you deal with those kind of things?
So at CCI, we work in 3 environments. We have fossil industry, which doesn't have stringent requirements, just relies upon us to pick the right material. Oil and gas, which has stringent corrosion requirements and extensive certification requirements. And nuclear, which is far and above that. So we are doing some experiments with Velo3D and one of our major customers in the oil and gas sector to see if we can come up with a strategy for providing the necessary certification requirements. And there, Velo3D has been a great partner because of the consistency of calibration and systematic approach which they bring to the methodology of certification. So but that's in the very early days. I think that's probably a couple of years away before that gets sorted out by the industry. And we see customers asking for 3D printed parts, and we have to discuss this issue and how much do we give, how much do we back off is kind of an open area of discussion at this point in time until the standards are in place.
No, there's definitely like a lot of people working on standards of their own sometimes as well, which I think is really terrifying. But also just conjunctively to organization, which I think is a little bit more, makes me a little bit more comfortable. But and we don't want this balkanization of these standards, right? That all of a sudden nothing's going to be interoperable or that kind of thing. I mean, are there also challenges? We have one question for the audience. I think it's a very optimistic question about somebody asking, what are limitations faced when mass production of metal parts using additive manufacturing? So then we're getting a little bit further. We're getting past the certification hurdle, and then we're already like, this person wants the mass produced parts. Is that something that you guys are thinking about? Like Jose, is that something you guys are really excited about, or are you thinking that that's not going to be, or is that a very, very far away kind of thing? Or maybe Zach wants to have a stab at it, or I don't know.
Yeah,
it is it's a kind of like future perfect question. You know what I mean?
I'd love to, honestly, because I think that's one of the things that we see as a major barrier to adoption for metal additive is, the supply chain flexibility that I mentioned earlier. I think, one of the things that we've seen as a challenge is that there are people who are good, who have proven themselves very capable of kind of getting the legacy additive machines to do what they want them to do. And these are distributed throughout the world. And if you have a single part that you want to go into mass production with, one of the issues you run into on a supply chain side is that you then have kind of these unique snowflakes of process parameters and workflows and everything else that you have to essentially certify on a one-by-one basis. And so we're trying to work with all our customers to make sure that you have scalability already built into the manufacturing process, at least the part of it that we control, where you can take, essentially a single build file for a given component from an OEM and have that produced anywhere in the world on one of these systems and end up with something that you have confidence in as having the same result, the same output. And that requires, complete system calibration tools, the management of the digital workflow and the thread that runs through that whole thing, and the ability to validate what happened during the print while it was occurring. And so that's, I think, a critical aspect of scaling that the industry is only now, I think, starting to address in any real way.
I think it's interesting that you're only part of the process. I mean, I think it's really exciting. One of my big coin drop moments years ago was when somebody was like saying about an aerospace application, oh, we make the shape on the printer, we make the part in post-processing. And I was like, okay. And then the problem is they were talking about turbine blades, so it was a bit scary. And we've got two questions about post-processing. And one of them is about, can you expand on this finishing of AM parts? I'm curious how you specify the finish and what AM process you use to complete the finish. And someone else is just, how do you solve the problems faced in post-processing? I'd like to answer this in a bit more an integrated way. I mean, how do we make this part of the process, right? So we're trying to come up with a certified part at the end of the day. We have our file going in, we understand. We kind of want, or we have a requirement somewhere. So how do we bring all this together? How does this all get together with this post-processing? Does somebody want to try to answer that?
I'm happy to take that on, but I believe John Barnes is probably the best person to I'm going to volunteer you here, John.
Exactly. Well, Jose and Steve, probably better than me right now, but I mean, the way we view it is the process to qualify something as the process. Additive doesn't really change that. It's a different way of getting through the process, and it may throw some new questions that need to be answered. But, fundamentally, the process is the same. And so the post-processing is really part of the we don't even like, I now take umbrage at calling it post-processing, because in every other manufacturing process, we would call it part of the processing, so yes, we're making the net shape with the 3D printer, but we're finishing it with everything else. And I think, kind of hearkening back to Zach's point there, I remember when he first showed us, elements of the flow software, I remember we were so excited that we had information that would tell us whether we're in calibration or not. I mean, that was the state of the art, which is like ridiculous if you think about a CNC machining cell. Can you imagine not being in calibration? Like, oh, we don't know what we're making, but looks good.
Yeah, definitely. And I'd like to ask, I mean, we did start this, like we've gone, I think, throughout the entire process, like from the beginning to the end. We talked a bit about the design and tracking this kind of thing and all this. Do we believe that DfAM is here to stay? I mean, I think John has definitely kind of said at the beginning already, like DfAM is something we have to do because we have to do it, kind of? Or do you believe it's going to like generally disappear? Is this just like a learning curve thing and this is going to disappear, or?
So I want to, I would defer to Jose and Steve on this, but I think that DfAM itself, DfAM is here to stay, designing for the manufacturing process. Hopefully what we're seeing is advancements in the printing technology minimize the steepness of that learning curve. So that's my take on it.
I have to say that I agree. In fact, that's a little more generic. Design for manufacturing is a key driving goal of people like us right now that are trying to figure out how to introduce, again, a small number of prototype units, small lots as first production runs, or even if they are production runs, but for industries that do not require thousands to millions of units, you definitely have to focus on cost minimization. And that cost minimization comes even from a reduction of part count. So it's not even a matter of where we're looking at a specific part. How did we make it? We need to, if it is a global approach to say cost reduction and expediency and flexibility of design and delivery of a unit, design for manufacturing is here to stay. Now, design for additive manufacturing, well, I agree that it straddles a little bit both. It is a learning curve, but it's also partly here to stay. There are potential limitations to additive manufacturing that still need to be explored. And I want to take advantage of the fact that I read one of the questions that was directed at me. And Joris, you already flagged it as something that you would like to answer. From Clay Lambert asking, what is just over the horizon in terms of what is compelling in terms of tensile requirements. And that is a topic I touched upon with you guys in our pre-meeting chats, that we still need to know whether the materials that are available for additive manufacturing, even though they're analogous to bulk materials like forgings and castings, whether they will share one-for-one the mechanical properties of their bulk counterparts. Particularly in the field that I'm in, again, when my slow impellers rotate at 60,000 RPM and my fast impellers rotate at, say, 350,000, we're talking about small refrigeration compressors or turbochargers, but imagine the conditions are extreme. I cannot take at faith or blindly a risk that my additive manufacturing material is going to be just as good as something that has been true and tested for the last 150 years. So before I dare to answer what looks compelling as ready to be addressed in terms of turbo machinery, I can tell you that we're already doing some legwork in collaboration with Velo and in collaboration with other partners to characterize the mechanical properties of particularly Inconel 718. It's one of the easiest super alloys for us to deal with, and we need it a lot. So we have done tensile, ultimate, and 0.2% yield stress analysis on a relatively sizable population of 108 samples. It's pretty big for tensile and mechanical properties in general. And we're already working on creep and fatigue analysis. Of course, these experiments are more expensive and we'll have fewer samples, but this is what's going to buy me the confidence to incorporate this in, say, high temperature turbo machinery, the hot side of a gas turbine engine. Right now, I have confidence I can use the technology on the cool side, on the compressors, on the blowers, on the air cycle machines used in the aircraft industry to handle the air conditioning and cooling of an aircraft. But the gas turbine side, where you have gases coming in on the low end that say 1200 degrees Fahrenheit all the way up to 2600 degrees Fahrenheit, well, that is a risk that you cannot just say, yeah, we can make it out of 3D printing material. And that's where extra research is needed and potentially designed for additive manufacturing. One of the things that we're doing with the Air Force, and I will just wrap up my thought with this, is that the radial turbo machinery that we're designing with in this Air Force program attempts to incorporate, because of the ability to use Velo's 3D printing process, we're going to incorporate for the first time internal cooling in a radial turbine. Internal cooling is normally used in large aircraft in axial blades, but those are extremely expensive. We're talking about a big GE90, for example. Each little blade on a turbine that maybe has 70 blades costs upwards of $25,000. We don't have that cost breakdown when we're making a single drone engine. So our wheel still needs to be inexpensive, but we are going to incorporate internal cooling to extract all of the extra efficiency that we want from a turbine and to increase the safety margin of the material. So again, this is also a little bit not only leveraging the ability that 3D printing or additive manufacture gives us, but also assuming that the materials may not be necessarily as strong as their bulk counterparts. And that's what we want to introduce is internal cooling. Until we know better, more mechanical properties are available, we'll be able to expand our horizon. Other alloys are coming online. Zach, I am extremely excited about the possibility of guys printing these same turbine wheels for us out of Haynes 282. So please have it ready as soon as possible. We really I'm saying this publicly because I know that it is customer interest that's going to drive this availability. So I'm sure that there are others out there who are looking forward to higher strength super alloys to come online. So that's it.
Oh, definitely. And I think so, Steve, for your, if you're looking at your journey right there, I mean, I think how has it been what have been the most difficult things for you? What have been the most like the most successful things for you, and this whole journey into additive?
That's a really good question. One of the most difficult things I think Zach touched on, I had a production manager ask me, can I print bars? says, why would you want to print a bar when you can get it off the shelf someplace? So there's a misunderstanding about where and how to apply additive manufacturing in the right place. I say the best things have been we have field proven performance that provides a customer advantage. We've had customers install these parts and their plants run more efficiently and run better. And that's been very satisfying to me, because usually those performance complaints ultimately come back to me and my engineers anyhow. So that increase in customer satisfaction is what I was really seeking with additive manufacturing. And that's been the most satisfying part of it, in addition to the cool shapes and geometries, which we also get to make.
Oh, we definitely, it's all about making the cool shapes. And
Yeah.
I think one interesting thing, I don't know if you guys can answer this, but like, so typically what I used to tell customers, I always say like, okay, if you buy a powder bed fusion machine, it's going to take you like 6 to 8 months to kind of reliably get stuff out of it, right? And then you count on investing like about 2 million, and then in all the HVAC and all the stuff you need, and then you're off to the races in a year with 2 FTE, right? That was my kind of like, I would say that in the first meeting just to scare off the people in the beginning, because otherwise it's not going to be useful, right? And has that equation changed? Do you think it's easier now to enter this market as somebody with needs or somebody looking for a solution as a customer?
I'll speak for CCI. We looked at it a couple of years ago, and in our view, it was better to keep it to work with qualified suppliers network, because we just, even though we could have maybe found the capital, the manpower, the skills to need it to do it right, we didn't feel was a good fit with our organization. So we're very happy to work with a really good quality network of manufacturing suppliers for this material.
Yeah, no, totally. I think it's a very exciting way to go for a lot of people. And I think it's a good point. The people, like what a lot of people don't know is that a lot of these people you can't find, right? You can't find a very good like plant manager type of guy, or somebody who'll do your what do you call it, a management system for additive. Good luck, have fun. I mean, there's these people that just like, we used to sell like, I don't know, it was like 10, 15 years ago, we sold like 100 printers a year, maybe, So there's just, and most of those go to universities at the time. So there's like, or like, very few companies. So there's very few people out there that can do the work. So I think that's a really good point. There is a very clash for talent.
We always,
how about you?
We always kind of tell people that, if you're not making parts today, 3D printing really isn't an invitation to start doing that. It's complicated and it's a discipline. It's hard to make parts.
No, definitely.
That also kind of plays into our philosophy, right? I have in my background here the manufacturing floor for Duncan Machine Products, which is one of our customers. And one of the things that we like to do is to find people who are really good at making stuff first. So precision CNC shops and people who have kind of the entire workflow, the QMS, everything that you need to really make quality parts for your customers. And then add additive, add the Velo system as another part of that toolkit. And in that way, you can leverage all of the infrastructure that's already been built. I think John's completely correct. If you start from scratch, it can be a challenging process, but
it's an opportunity.
It is a challenging opportunity. But if you have, people who have that expertise, I think you can grow into it. And one of the things that we try to do as a company is to kind of democratize that ability. And so you see people like Vertex Manufacturing post about their ability to install a system and have it running production parts in a couple of weeks. That's building on the infrastructure they already have, but I think it's becoming more mature as a technology in a way that makes that a little bit easier than it ever was before.
Yeah, I mean, let's be honest. Vertex is probably on the +3 sigma side of experience.
No, I think that's it. No, it is true, but it does attract quality people because you have to be in control of reducing variables and putting stuff out the door to even attempt this in a really good way. I think so. You're going to attract these kind of people to this game. I do think it's if you're very good at something, if you do things, then for example, this could accelerate your adoption of a new technology. And if you're the kind of company that doesn't want to be making stuff, like not even that you're not making stuff, but you're not into it, you're not like all about that, then I think it's going to be a very difficult path going forward. I think even though we'd like to keep it all rosy, it's just like you push a button and then you know, like all these people you see smiling next to their machines. There's not a lot of smiling next to the machines. Usually it's a very serious kind of thing, really. Is there anything that somebody wants to say and thinks, oh man, I didn't get a chance to say that? I think that's a good practice to always kind of throw that in there just in case I left something out or didn't give someone an opportunity. I think one quick question for Zach is that Glenn Desmier asked, is pure copper available? That could be
pure copper is not yet available, but right now we are working on GR Cop 42. So if you're looking for good thermal conductivity, that's a pretty decent alloy to consider.
Yeah, that's the NASA copper, right? That's yeah. Okay,
Yeah.
Cool. Sounds good. Okay, well, thanks for that little question. I thought it was really fascinating, really good. I thought it was nice and realistic, guys. I didn't see any kind of like over the top crazy. You should go buy a machine now and make a million things tomorrow. I think that's really nice. I thought it was really exciting what Jose is doing with making the shrouded impellers. And there used to always be this demo part. You guys don't even know like the joke about having someone on your show that actually showing an impeller. It's funny. It's kind of funny because it used to always be like a demo part. Everybody would have an impeller because it's a feasible part, but there weren't like, just like everybody had these conformal cooling channels, but then there weren't very many people that were actually doing it, you know? So I thought it was really good that we're actually making impellers and actually making them for customers, not some pie in the sky project. So I thought that was really exciting from Jose and from Steve. I think it was really exciting that they make these really critical valves and they're doing so many variations of them. Like they're doing so many thousands of new ones and so many different markets and stuff like that. I think that's very exciting in a valve application. That's something that had not been considered by a lot of people, apart from maybe actuating kind of in those kind of valves. But these kind of valves are a hugely exciting market for me too. And I think, you know, optimizing the geometry and mass of these things could become a very exciting thing for IMI as well. So that to me was good. And yeah, John was nice as always and thoughtful. And then Zach was great as well. So I really enjoyed this. I did. And I hope that the audience really enjoyed it. Thank you so much for your attention, first off. Thank you as well for your questions that we got to answer. I'll see if I can get to some of these questions offline to some of the people. And we can answer them. And thank you so much. And welcoming your additive journey. If this is a new part here, I think this is a good place to start. And I hope you learn a lot and get your hands on some parts very quickly is always my advice. And I hope we can help you in some small way. And if you're a bit more advanced and everything like that, I hope we were able to teach you something as well. And thank you so much for your time, everyone. And thanks and have a great day.
Thank you.
Thank you.
All right, bye-bye.
Thank you. Bye-bye.